Okay. Okay, well, good morning, everybody. Thank you very much for the introduction, and thank you very much to the organizers of this very interesting workshop to invite me to present this work. This is basically related to the PhD work of the first author here, Christos Lataniotis, my PhD student, and this is a joint work with my colleague, Dr. Stefano Marelli. So, as it was said, I belong to the chair of risk, safety and uncertainty quantification in ETH, so it belongs to a department of civil engineering, and this is more or less our motto. So we address all kinds of problems related to uncertainty quantification for engineering applications and also beyond engineering, with a number of topics: structural reliability, global sensitivity analysis, model calibration, reliability-based design optimization, and more. So these are lists of let's say, topics we are currently investigating. And then in terms of applications, we belong to civil engineering, so there are a number of problems coming from civil engineering, typically structural and geotech, dam safety, earthquake engineering. But then we also develop a number of collaboration outside, because as you will see, all the methods we developed are in essence non-intrusive and somehow independent on the field of application. So we have a number of past and current collaboration in mechanical engineering, hydrogeology, remote sensing, computational dosimetry, and even more recently macroeconomics and astrophysics. So this very far away from the original application. Okay, so today I'm going to talk about surrogate models and with a focus on high dimensions. By the way, we also develop MATLAB-based software for uncertainty quantification. So if you're more a MATLAB person than an R person, you probably find interesting modules and packages in this software to do, well, different kinds of analysis I've mentioned already. Okay, so we consider basically simulators for engineering application as let's say black box models that basically contains different ingredients. Of course, some governing equations, mathematical equations, depending on the physics of the problem, but then also solvers to those equations. So we really consider a simulator as a black box, as basically an unknown function that maps input parameters to some output quantities of interest. And then those computer simulators can be used for various purposes depending on the topic. It can be used, well, for instance, to be able to reproduce experiments. So this is the whole field of calibration. Bayesian techniques for calibration are used in this context. In the context of engineering design, it can be used to explore the design that is varying parameters and see how the systems you model with your simulator would perform under different conditions. And then you can put this into an optimization loop to really optimize the design of the system, typically in mechanical engineering or aerospace. Minimizing the cost means minimizing the mass, but still performing or satisfying certain performance constraints. Okay, so this we represent in a quite, let's say, popular scheme in which the starting point is really the black box simulator, for which there are a number of input parameters that are not well known for all kinds of reasons: lack of information, variability of data, variability in time, and things like that. So we represent those inputs in a probabilistic framework here, typically by a joint random vector for all the parameters. So this part here is for real applications very, very crucial, because if you don't make assumptions about the distributions that really fulfill the knowledge you have or the data you have, everything afterwards can be completely wrong. Then, well, we are mostly interested in uncertainty propagation, that is to understand how the uncertainty in the input propagates through the model, and then to be able to derive some statistical estimates of the quantity of interest, typically performance indicators of the system that is modeled. And here we may be interested, depending on the problems, on the full PDF of the output, on statistical moments, on probability of failure. This was mentioned yesterday in the talk from Alex Diaz. The field of reliability is related to computing small probabilities of failure events. And also very often we are interested in sensitivity analysis, so that makes a link with the previous talk. It's really how to define or how to find in a case with large dimensional input, how to find the active variables, the important variables for UQ. So this being said, now we work with more and more complex simulators, meaning that a single run can take hours, even days. We have a recent examples I mentioned, astrophysics. Those guys do ab initio model of the universe, so really dynamics of particles. And a single run, once the parameters are set, a single run is about 5 years of computer time. So on a big cluster with 20,000 cores, it's a few hours or a day. But in total, it's matter of really years. So this is something done in collaboration with the University of Zürich right now. So of course, this being said, we cannot use Monte Carlo simulation to then propagate the uncertainty from those input to the output. So that's why there are different ways of constructing surrogate models, which will be basically approximation of the original very complex and costly simulator that mimics this feature. So it's generally based on the same procedure. We define a limited set of experiments, a set of computer experiments, experimental design, and then we assume some regularity in the underlying black box model to choose a family of functions, let's say, that we can somehow fit to this complex simulator. So here I've listed a number: polynomial chaos expansion, low-rank tensor representation, Gaussian processes, support vector machine, neural networks, and so on and so forth. So the point is that all those approximations here depend on some parameters, and the goal, of course, is to fit those parameters based on the runs of the real complex model. In the end, the idea is that these kind of simple functions are now really easy to and fast to evaluate, and then you can do Monte Carlo simulation with this kind of representation here. I mean, 1 million runs of this model, it's just a matter of seconds. To fit those surrogate models, again, we usually select an experimental design in the input space, which tries to cover at best this input space. So typically, optimized Latin hypercube sampling are used. Then we run the model, and then based on the input and output relationship, we fit the coefficients of the surrogate with the proper learning algorithm. So I call this generally here a learning algorithm, because it's very different depending on the type of surrogate you are using. If you do polynomial chaos expansion, you have all the sparse grid and stochastic collocation approach, which somehow consider specific points and then combine the results. You can do this by least square, by advanced least square and compressive sensing. And then if you use other techniques, of course, they have their own methods to fit the parameters. In the end, very important as well is to validate the surrogate. You introduce an approximation between the true simulator that is costly and this approximation. So you want to make sure that some error is mastered, and typically, if we want a surrogate model to work over the input space, the mean square error is a good measure. So what happens now? This is really the starting point. If we have, let's say, a few tens up to maybe 100 parameters in this setup, I would say we have mature techniques to solve those problems. Typically, sparse polynomial chaos expansion up to those dimensions, or low-rank tensor representations. That's the goal, and that works quite well. Above, if it's like 10,000 inputs, this does not work, obviously, at least today. But there is more than that. Now we have also many problems in which the input is not just a set of parameters, it's functional input or unstructured input. You can think, for instance, about time series when you have not just a parameter, but a time variant parameter, which is, for instance, climatic load, temperature history, wind velocity, depending on the problems. You could also imagine problems in which the input is not even a series, it's a map. For instance, when there is some kind of geometry, I think about the modeling of the land elevation when we do river hydraulics, or for instance, the rigorosity of a surface when we do some kind of contact problems. those are inputs that are basically not just parameters or vectors of parameters, but really more advanced things. So I have this example that I will address in the end of this talk. We are interested, for instance, in earthquake engineering, in modeling the structure of a building by finite elements, and then we are shaking this building by putting an input accelerogram at the foundation, and then we compute with all kinds of nonlinearity in the model the horizontal displacement, and then the maximal displacement is related to the damage, basically. So this kind of problem here obviously has as an input kind of chaotic time series, input time series, which is a real accelerogram. So if I consider, let's say, naively those inputs, now we have typically, well, to describe a time series, typically thousands of time instants. To describe a map, maybe 10 to the 5 pixels. And more than that, in contrast to usual UQ, where in my scheme, basically the input, the probabilistic model of the input is to be given before propagating the uncertainty. Here, we don't even have this model. So we may imagine, for instance, a catalog of recorded signals in earthquake engineering. That's the real data. And it's very difficult to really make a probabilistic model out of this, which, for instance, would allow to simulate new samples of such earthquake signals. So it's possible, but it's really not easy, and in any way, it's high dimensional. So this leads me to the point that if we want to further develop the surrogate modeling techniques for these kind of problems, we have to couple this somehow with dimension reduction. And that's the purpose after this long introduction. The purpose of the talk is to, well, give some hints about how to do this, dimension reduction on the input data, and how to couple them or to combine them with the standard surrogate modeling techniques I mentioned. And I would like to show, well, first that let's say this just sequential approach is not necessarily a good idea, or for sure it's suboptimal. And then I will show how we can couple the two in a more efficient way. So what I call dimensionality reduction in this talk is really concerning just the input, assuming that the data is a very high dimensional here. So data are realization of supposedly a high dimensional vector in Rm, and we want to represent this by a smaller dimensional vector z through a transform here, which will basically reduce the dimension while preserving certain properties of the data, the information content. So depending on the techniques, of course, this kind of method has some parameters that have to be inferred again from the data. Typical methods used, and that really comes mostly from the machine learning community. Well, principal component analysis, I think in this community is very well known. Kernel PCA, it's a kind of nonlinear version of this that really comes from machine learning. And then we have autoencoders and many other exotic ways to do this kind of compression. We sometimes also need the inverse transform. So once we have the compressed data, sometimes we need to recover at least approximately the original data, and I will use this notation X tilde to this so-called pre-image or inverse transform. How to combine this with I mean, my goal in the end is still to surrogate a complex simulator. So we could think about just doing this sequentially. You start by taking your data, you take a few or the best available dimensionality reduction technique. This brings you to a z, and then each x was associated to a y. Now you associate to the same y the input or reduced or compressed input z, and you have a link between z and y, and you try to build a surrogate now in a reasonable dimension. This does not necessarily work well. Sometimes it works, but in fact for very smooth problems, but in most cases it does not work. Here it's just an example here from some data sets. I just forgot what it was exactly, but we apply basically from different subsets of this set. We apply different compression techniques and plot here the reconstruction error. So this is on this axis the quality of reconstruction, and then we build surrogate Kriging surrogate model, and this is the quality of the Kriging predictor. And you can see that I mean, there is no correlation between the two. So you can have here a poor or in average poor compression techniques. This is here a PCA, but in some cases get anyway in the end a good recovery, a good prediction error for the subsequent Kriging model. And in contrast, you can use K-PCA, kernel PCA, get very good or very small reconstruction error here, but still get a very bad prediction. So these are disconnected. So because, well, the things should be in fact combined. So how to combine? Well, the idea would be that we have on the one hand the compression, which has its own parameters W. We have then parameters of the surrogate model, and somehow we should optimize the two for a given objective function that I will describe later jointly. And in some sense, that's the most recent machine learning technique do so. So what deep neural networks do, they stack basically layers of neurons, and basically it works with really high dimensional input and output, because part of the network or some layers are basically targeted to decrease the dimensionality in the kind of autoencoder fashion. And then you use also a neural network to then do predictions, but this is embedded in a single framework. There is an extension or let's say parallel with deep Gaussian processes where again the same things are used, but all these examples, I mean, they are not in the context of UQ, so they look similar to our point of view, but it's for different purposes. So what we want to do here is really to do surrogate modeling of complex simulator by combining somehow efficiently the two kinds of approach to in the end be able to solve the problems I mentioned in the introduction, but also to have really a general framework that allows you to freely select which kind of method you put in each block. Okay, and this has to be in the end data driven in the sense that we will well, use experimental designs and limited data to do this. So let me first give a few words about dimensionality reduction. So principal component analysis, probably I don't need to define what it is. We just take the matrix of data, compute the covariance matrix, do an eigenvalue decomposition, and just take the highest eigenvalue and corresponding eigenvectors and somehow project the original data onto the subspace spanned by those eigenvectors. So this is standard, very standard, and this is a linear transform. That is probably the most simple way to reduce dimensionality, and for sure you should start by this. So an example here, we have a number of trajectories here. These are realization of given Gaussian process. Instead of considering this data here as n trajectories sampled with maybe a few hundred points here, you can, doing principal components, you can just extract the eigenmodes of those curves and then represent each curve as a superposition of maybe 5 to 10 eigenmodes in the case where it looks very regular like here. Then this is in practice not sufficient, and again from machine learning people have extended this to the idea of kernel PCA. So it's a kind of nonlinear extension, at least in my understanding, in which you, as often in machine learning, you map your data into another space which stays abstract somehow, what they call feature space, and then you would do principal component analysis in that feature space. The problem is that this feature space is actually related to a kernel you will choose for your analysis, so it's infinite dimensional. So the trick is that the eigenvector in this feature space you can basically represent like this as a function of the transform data, whereas here phi is never really explicitly given, and all operations to do the eigenvalue decomposition involve in the end just inner product in this feature space, which is exactly the kernel that is defined to that is used to define this feature space. So in the end, it boils down to again a standard eigenvalue decomposition related to the gram matrix of the data given a particular kernel function that is now of your choice. So that's the way you introduce more, let's say, versatility in the framework, because now K is your choice. Okay, And once you do this, how to compress the data. So this is now the way you obtain the data. You again project the original data in the feature space onto the eigenvector in the feature space. So both of them you don't know exactly, but when you do all the calculations, it boils down to something related to the Gram matrix. So somehow it's not so different. It's kind of an extension. The big difference is that now the reverse problems, the so-called pre-image problem, is actually not as trivial as in regular linear PCA. And this is an issue in itself. You have to find a way to do this, to bring back, if you need it, the z's back to the x's. Just here a list of kernels I will use in the application. So polynomial kernels here with like few parameters, isotropic Gaussian or radial basis function, this kind of Gaussian kernel with a single parameter, and an isotropic Gaussian in which you have one parameter for dimension, per dimension. So just for the sake of compressing data, of course, now if I introduce this new three parameters somehow, I have to optimize them, and so I have to give a matrix to explain, to define what is a good dimensionality reduction. So there are two standard metrics, that at least the one we use here. One is called distance preservation. The idea is to find or fit, given a kernel, fit the parameter of that kernel such that you globally preserve the mutual distance of the points from the original space x to the feature space. That is basically the distance between the Euclidean distance in the original space and the one in the feature space. And again here, although we don't specify phi, this can be computed from the Gram matrix. Another popular way to do this is the so-called reconstruction error. So this is the idea that you take your data, you compress according to, let's say, kernel PCA for some given W parameters. These give you some Z, and then you try to recompute a so-called pre-image of the Z and try to make sure that this pre-image is close to the original point. And here, of course, this must be an approximation, because going into this feature space goes into an somehow infinite dimensional space. So you don't have a unique inverse solution. So popular technique again here is to try to make some kind of regression to get in the backward direction, to get an approximation of the x's, now knowing the z's, and here kernel ridge regression is used. Again, it's kind of standard with a kernel for this pre-image problem, which can be another, not necessarily the same one as the one used for the forward compression, but in practice, for instance, as in scikit-learn here, it's in fact the same. Okay, that's one ingredient. Now, how much I have? 10, 15 minutes? No, should be okay. Surrogate modeling. Well, this I will go very fast, because I mean I guess most people here know this. There is a full list of things that we could use. In this talk, we will use only Gaussian processes. So in Gaussian processes, basically, once you actually, I should have put these everywhere, because now we will do those Gaussian those surrogate models in the reduced space. So in Gaussian processes, we typically use universal Kriging predictors here with some regression part here, some trend, some non-coefficient, and then some Gaussian process with selected autocorrelation function with some parameters theta to optimize here. As it was shown many times, then you can condition this Gaussian process on the observation of your problem, and get a mean predictor, which will be the surrogate models, and also the Kriging variance, which gives you a local error. If you prefer polynomial chaos expansion, so here, the background is quite different. The idea is that you want to represent or to expand the function, really, that maps the input to the output y in terms of a series of multivariate polynomials. Those basis functions here are obtained from univariate, from tensor products of univariate orthogonal polynomials. And the big difference with Kriging is that, well, this orthonormality for the polynomials means that you have some measure on the data. So if the input parameters are independent, basically you build up your orthogonal polynomials for each input parameter separately. In the context of what I'm talking about today, where we will use reduced data Z and possibly, well, with unknown underlying measure, there is something to do as well to be able to apply PC. Again, there are many ways to then compute and fit the coefficients. Here we will use, in this presentation, standard least square if we are in low degree, where typically we consider that the full series is a truncated series plus a residual, and then we basically minimize the residual in a least square sense. Of course, in practice for high-dimensional problems, this does not work, because if you have many coefficients here in this expansion, then you would need even higher number of points to compute those coefficients. So we use basically sparse polynomial chaos expansions with algorithms such as least angle regression or orthogonal matching pursuit that basically finds jointly what are the non-zero coefficients in a possible big candidate set, and then computes those coefficients. Okay, so sorry for those of you who are not familiar with either of these methods. That was not the point to explain the details of this. This is really quite standard. Now we want to really couple this with high dimensionality. Yeah, so that's basically maybe the important slide. As I said, just doing dimensionality reduction first, then surrogate modeling is either does not work at all, or at least is suboptimal. So we want to do something like that. We want to reduce the data or compress the data into a medium dimension space, and then do a surrogate model. But we want to basically optimize the parameters of the reduction in such a way that the obtained reduced variables are suitable for a nice surrogate model. So it's not just for the sake of being very good in compressing and that's it. It's finding W such that when you put this into the loop, then let's say prediction error between this and this going this orange path is good. Okay? So, well, this is a joint problem in which we have two sets of parameters, the ones from the compression, the ones from the surrogate model, and we want to minimize some kind of loss function or error between the original function and the surrogates based on the compressed data. If we again work based on data, we can typically use as a loss function a mean square error between the on a given validation set between the points with the real evaluation of the simulators through the blue path here and the value obtained through the orange path. So we will use a global optimization to solve this W, and now in each step, given the W, we have, so given the W means that we have the current reduced variables, we will apply standard techniques to solve, to get a surrogate model. The thing is that constructing this surrogate model M-tiled for a given W is within a loop on optimizing W, okay? So that's why at this stage we cannot do, or we cannot use the most advanced fancy techniques we have, otherwise it would just last forever. So here typically at this stage we will use, if we use Kriging, we will use a simple kernel, isotropic kernel, so that we have only one parameter to optimize, or we will use low degree, typically low degree Legendre polynomials if we use PC. Once this has converged, so optimizing W such that this error in the end is small enough, then we basically consider that we have the optimal dimensionality reduction for the sake of subsequent surrogate models. And then now at this stage, this final stage, we use the best surrogate we can have. So I call this high accuracy, meaning that we will use Kriging with typically anisotropic kernels and more advanced optimization algorithms to find the hyperparameters. Or we will use adaptive sparse polynomials, and here I put the word arbitrary because now we build this PC based on the reduced variable, the optimally found reduced variable Z, which have whatever distribution. So we basically will use polynomials that are orthogonal to this distribution of the input parameters, but this is not analytically known, so we need some kind of estimation of the density of the Z's to do so. Here it's just a graph basically explaining what we do. So we start with the original data. In each loop, in each iteration of the loop, we compute the reduced variable. Generally speaking, we would split it into training and validation sets, train a surrogate, and then compute a validation error. And that is given W, and then we have this optimization over W. In practice, if we use Kriging and PC, and that's the reason why I used them here, because anything else could have been done as well. But if we use Kriging or PCE, we actually don't need in practice to split the data into training and validation, because we can evaluate the mean square error through so-called leave one out cross-validation, which is a way to basically just solve one surrogate and then analytically get an estimation of the error without the burden of really splitting between training and validation. So that's what we use here. There is a remaining parameters that I did not discuss. All those techniques for dimensionality reduction have parameters, but also you choose how many components you want. And so basically the dimension of the reduced space is also a free parameter. So what we do here is that everything I mentioned, we basically do in parallel for different dimensions, a number of dimensions. And in the end, each optimal solution has its own mean square error. So we select in the end the best dimension or the best reduced space based on this. Usually the curves look like this. That is, if you take just a few components, the resulting global error is big. But then it decreases, but at some point it decreases again, and there is an optimal. Okay, so these are, now I will show just some results. So the ingredients of all this, there are many in fact. So we need some dimensionality reduction techniques, some surrogate modeling, some error estimator. This is this joint mean square error in the current context, and then some optimization techniques. And in the applications, as I said, the framework allows you to put whatever you want in each box. We mainly investigated in the presented results now kernel PCA and PCA, Kriging and PCE for surrogate models, and the error by leave one out, and optimization, this loop over the W parameter using global optimization genetic algorithm with a local gradient-based refinement. First application is actually of the kind of the ones I mentioned before, where it's a simple map between inputs and outputs, but in high dimensions, with the idea that there is a small effective dimension. So this is a problem addressed in this paper here, and we got the data directly from John Jakeman at Sandia, who gave us really all the simulation they used for their paper just for the sake of comparing methods. So this is the idea that you compute some voltage in such a circuit here, and basically you have many resistors, but what counts in practice, or the effective dimensionality, is related just on the few ones that are close to here, close to V0. So we have here a problem with 80 dimensions, and we addressed it with the sequential method, that is compressing somehow the data related to 80 dimensions and then do surrogate models, and then jointly do this with 500 samples for training and 500 for simulation. If we do the combined approach that is shown here first, so optimizing the dimensionality reduction for the sake of a better surrogate model, it appears that basically in that case the best way is to use kernel PCA with an anisotropic Gaussian kernel, and well, it's quite equivalent if you use Kriging or PCE, and it gives you somehow 20 components, 24 components, 8 here and 24 here. And that's the result. So those plots, you will see a number of them. It's the root mean square error of the surrogate now on a big validation set. On the left, you have this DRSM, so that's our combined approach. And on the right, each time, this will be what you would obtain if you first and independently do first compression and then surrogate models. Here, obviously, well, it's clear that this works and this does not work. It's not necessarily surprising. What we try to do in these three examples here is to compress some data, which actually is not really compressible because it's 80 different independent parameters. So if you look just at x, there is no structure. There's just 80 different independent parameters. So if you try to compress something and then do surrogate models, that does not work. But if you try to do this jointly, you can interpret this as a way to solve for standard parameterized problems, to solve solution in a very high dimensional input space, because you compress the data for the sake of finding the active dimension. So that's exactly what happens here. Now another problem with really high dimensional things. So here it's 1D elliptic SPDE, and again, in the end, we have in mind to solve problems in which we have data-driven input. So here we have an input. Actually, it's not Gaussian. Sorry for this. It's a log normal random field that was used for the calculations here. But we consider that we have pre-computed realization of this input, let's say, diffusion coefficient field, and the corresponding output is u of 1 in that case. And then we consider just this data. So as such, this data is a set of trajectories, here again 500 trajectories, and each of them is discretized with 200 points. So it's, as a raw data, it's 200 dimensional. So we try to use the combined framework. We try to compress the data in a way that the subsequent surrogate model that basically links what it is, u of 1, so the solution here of the problem at the right boundary as a function of the random diffusion coefficient. This in that case, we also combine different compression and surrogate modeling techniques. The best one, obviously, is when we use PCE and when we use a polynomial kernel for the compression. And that's what we obtain here. If we use Kriging, our joint model gives the best error. If we use kernel PCE plus then sparse polynomial chaos expansion, you see that basically our, let's say, results here are exactly similar to what you would do in a classical setup, that is first compress the input with principal component and then do surrogate. Well, that's really not really surprising. For those kind of problems, that's exactly where a standard PCA works very well, and that's why we do this. Here we basically don't improve. Probably I have 2D examples where it's slightly even not so good. I mean, the standard or the basic sequential approach would be better. But the problem is, it's not a problem, it's a feature. It works very well because of the problem here. It's an elliptic SPD. It's kind of regular compared to the other problems we have in mind. So here we basically bring nothing, but it's at least as good. But then now, at least for this last problem, we can do with the joint with the joint modeling, we can address problems that are, let's say, much more non-regular or non-linear. My last example, and I will close with this, is this earthquake engineering problem. So you have a finite element model here with beam elements, all kinds of non-linear behavior of the material, because when you shake this kind of building, it does not remain elastic, of course. And you shake this with this kind of inputs here. And we have a full catalog of input ground motion here, 10,000. Each of them is sampled at 50 hertz over a minute. So the raw data, again, is 3,000 dimensional. And the output here, it will be after running the finite element and seeing how it shakes. The output would be the maximal displacement between stories, which is directly related to the damaging onto the structure. Well, here, this 3,000, actually, we were a bit ambitious. We did not manage to just apply what I said so far with this 3,000 input. So we put some kind of pre-compression, I would say this way. So we use the wavelet decompositions of the signals to reduce, let's say, the 3,000 real time instance and inputs to almost 200 again, which means that there is room to improve what we did, because directly with 3,000 and for this very nonlinear problem, this did not work. We also had many samples, so we basically also, just for the sake of being a bit parsimonious, we selected out of these 10,000 samples a few hundred to be realistic. And then again, we try to first compress optimally the data in view of subsequent surrogate modeling. So in that case, the anisotropic Gaussian kernel for KPCA gave the best results. You can see that, well, in terms of root mean square error, it's not so good. And then that's the kind of results we obtain. So in terms of global root mean square error related to the predictivity of this emulator of this complex finite element model, the approach is a bit better than the separate ones. But what is interesting is really not just the root mean square error, but really the scatter plot of the real the real simulator response versus the real emulator. If you try to do compression then surrogate modeling, basically, well, you are really not good in many cases. If you do the joint approach, although the global error, at least at this stage, is not tremendously good, at least we have something that is well structured. And we observe the same for PCE as a surrogate model. Again, we significantly improve this. So I think my time is over. As a summary, we proposed a new framework to coupling somehow efficiently dimensionality reduction and surrogate modeling, with the idea that these are two ingredients you would put together, but somehow based on your personal interest and I don't know, knowledge or just what you prefer, your preferences, you would like to put in each box really what you want to have, the kind of methods you want to have. We were able to do a few examples, let's say now up to a few hundred dimensions, so it's still not yet thousands or more, but we are on the way. And basically, now we want to continue or further develop this work in several directions. One is really to explore also new combinations. So, for instance, we just use so far Kriging and PCE as surrogate in the reduced space. We have other methods at hand, so we want to explore this. This optimization process to find the proper compression parameters, you see it's a kind of double loop. I think we can also do a better joint optimization at this level. And of course, in the end, we have this challenge in engineering applications that so far we are not really solving properly. With this, I thank you very much for your attention, and well, thanks.
Thank you very much. Are there any questions? There are a lot of questions. Sorry to start. I think you could first.
Yeah, so your root mean square error plots, as you add more of your basis vectors, they go up again.
Yeah.
So could you say something that I was worried about adding information and getting worse? Is there anything?
Good questions. Right here. I mean, I have another context where it's exactly the same, and I think that's the same answer. When you do a kind of sparse expansion, so typically you have fixed data, and then you want to do a kind of regression with a large number of terms, typically polynomial regression. Okay, if you just put linear terms, well, your error is not so good. If you add polynomial, second-degree polynomials, usually you have more terms, and you will have a bet. So the error will decrease if you put such more terms. If you put many terms, at a point you do overfitting basically. So you have the global error, although you have more terms, so higher degree polynomials, typically you would think, okay, it should be better. Given limited and given data, it's not better in the global mean square error, and here it's typically leave one out error, so it's really a prediction error, it's not an empirical error. Empirical error would always decrease, but the real error due to overfitting starts to increase. So I think that's the more or less same process here, I think.
So you mentioned the fact that you're uncovering the active variables in some way. Is it a byproduct of your technique? Because you're looking at the leave-one error, you're looking at RMSE? Mm-hmm. Or are you, in your algorithm that I don't fully understand yet, are you putting some effort into finding those dimensions?
No. The first example I gave is actually, let's say, the standard setup that we are used to solve. And we realized that applying this technique, which in the, we try to devise really for time varying input and so on, gives also excellent results. And my interpretation is that really it should not be understood as compressing the data, because here there is no compression to do. If you have 100 independent random Gaussian variables, they are independent, there's no way to, I mean, you cannot do anything to compress this into 10 variables because they are independent. But if the model depends only on the 10, the joint algorithms we have devised somehow finds the right 10 and do this. And it's a kind of a byproduct. I mean, this is not the reason why we develop this, but on such examples, this also works.
Yeah. So fundamentally, the active dimensions are a property of the underlying model, right? And hence the property of the data, not of the surrogate model.
Yeah.
Isn't that right?
Yeah. Yeah.
So presumably, if you have a surrogate model that captures the underlying model to a large degree by adding a huge number of terms in your PCE approximation, or refining that model as much as possible, then you should uncover the original active variables.
Yeah.
So I feel like what you're doing is sort of trying to get an active variable of a coarse model, and then to somehow jack up or get a better error estimate. But if you had a better surrogate model, then you should be getting the correct, in some sense, active variables. And
yeah, but in the first example I just mentioned, you can think in terms of many parameters and some active and some inactive or useless. That's okay. But that's not the point of this algorithm. The point is really when the model, the simulator, the input is not a set of variables, is a set of time series, for instance. And in this kind of data is either, if you take all the time instance, it's a huge dimension because you have 3,000 points per input. And it does not make sense to do a surrogate model in these 3,000 dimensions. In any case, it does not work. We have other works that shows that it does not work because the time-dependent output as a function, or at a given time as a function of the input series at a given time, there is no relationship. It's just noise. It's because those kind of systems or models really integrate the transient history, and you cannot just map the input at a given time to the output at a given time. There's no way to do this.
Right, but there's an underlying structure. You can find sort of.
So that's the way we try to find somehow to try to find some kind of feature in this high-dimensional input.
But the idea of coupling the active dimensions to the surrogate model, I feel like you're not getting the actual properties of the problem. You're getting properties of your fake model. And in fact, in your algorithm, you do the fitting of or finding the active parameters with a suboptimal model, with a very coarse model.
Yeah.
And had you done
no, I agree. Yeah.
Had you done it with a very fine model, probably you would recover the correct active parameters.
Yeah. Then it's just a matter of computational time. You're right. In the loop of the optimization, we can also use, let's say, low accuracy or high accuracy type of surrogate modeling technique. If you use the best you can do, it just takes much longer because it's within an optimization loop, and the results. But as we observed on the simple problems, the results are not tremendously better. So that's why we sort of degrade the compression within the loop, and then once we get, again, there is no unique solution. I mean, we are not talking about finding a unique solution of a given well-posed problem. It's standard simulators used in engineering with crappy data, and that's the state of the art. How people do this. So if we find a solution to surrogate these things, it's already good. And the only way we can claim we did something interesting is because we have this, heuristic mean square error on validation sets, which says, okay, it looks not too bad. So that's the idea.
I think in the last question, and then
if there is a break, then we can do this.
You already mentioned it somehow. I really liked the presence of APCE in the talk. If you make this PCA or nonlinear PCA, you usually have kind of a transformation that is nonlinear in form of history.
And give you a structure of data with whatever probability underlying.
How do you ensure that the APCE is an approximation scheme? in the sense of
Is
dense.
what?
It's an approximation scheme in the sense of to be dense in your underlying problem. Because if you have dependent structures, APC, then you get any distribution, and polynomials might not be dense.
Well, this like the previous version. Previous question. I don't know. I don't know, but I need to do something that is reasonable to do this. So it's a kind of heuristic. So indeed, we compress the data, which is already non-structured somehow for those problems, into now a small dimensional data, which is still unstructured. How do we represent this to be able to use our beloved PCE? Well, we take the marginals and fit some kind of distribution and use orthogonal polynomial to this, but there is usually dependence, so before this we also remove the dependence with some kind of transform. Does it always work, or is it always robust? Probably not, I agree, but that's the best I can do.
Okay,
Okay.
so thank you very much. I
Thank
think
you.
we postpone all the other questions.